Hi everyone, this is Dr. GVR Shashiro, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials. So in this subject, in the previous session, already we have discussed about slope and deflection of a various beams. So how to derive the equation for slope and deflection for a various beams we have discussed. In this today's session, I want to explain about different methods for slope and deflection calculation at a particular section of a beam. We will see. So the course outcome is, at the end of the course, the student should be able to utilize Maxwell's reciprocal theorem, double integration method, and the moment area method for determining. These are the determining the slope and deflection determining methods. The student should be able to answer this reciprocal theorem and able to explain about this double integration method and moment area method for determining the slope and deflection after completion of this module. So first of all, we will discuss about the slope and deflection definitions. So what do you mean by the slope and what do you mean by deflection? The slope, it is a angular shape at any point of the beam between no load condition and a loaded beam. So whenever the beam is subjected to load or without load, so that is the angular shift at any point. So that is called as the slope. Its value is different at different points on the length of the beam. It is represented by I or theta. So with theta or I, it is represented. Its units are radians. There is a maximum limit for slope for any loaded beam. There is a maximum limit. So what about deflection? It is the vertical shift of a point on the beam between load condition and a loaded beam. So its value is different at different points on the length of the beam. So it is represented by Y or delta. So units are mm. There is a limit for maximum deflection for any loaded beam. So suppose you take a cantilever beam. So whenever it is subjected to load, so the deflection is like this. So it means there is a angular shift, that is theta, and then vertical distance, that is y or delta. So this is called as deflection and the angular shift is called as slope. So there is a maximum limit for maximum deflection for any loaded beam. Now we will discuss about methods for slope and deflection at a section. So though there are many methods to find out the slope and deflection at a section in a loaded beam, and the following two methods are important from the subject point of view. One is double integration method and as in Macaulay method. So many methods are there to find out the slope and deflection at a section. In subject point of view, these two methods are important, that double integration method and Macaulay method. So it will be interesting to know that the first method is suitable for the single load, that is double integration method. Whereas the second method suitable for several loads. So whenever the beam is subjected to single load, then the double integration method is used. Suppose the beam is subjected to several loads, that is second method, that Michaelis method is suitable. So first we will see double integration methods for slope and deflection calculation. What is this method? So how to calculate? What are the equations how to derive? We will see. So in this double integration method. So the bending moment at a point. So already in previous session, we have derived this one m is equal to EI into d square y by dx square for simply supported beam. We have derived this one equation, that is bending moment at a point. Integrating the above equation and integrating the above equation once again, that is double integration. So we will get the equation double integral m is equal to a into y. So the bending moment at a point, that is m is equal to EI into d square y by dx square, and integrating and double integrate. So it is the obvious that after first integration, the original differential equation, we get the value of slope at any point. On further integrating, we get the value of deflection at any point. So first integration, the original differential equation, we get the value of slope. And second integration, we will get the deflection. So while integrating twice the original differential equation, we will get two constants. One is C1 and C2. So the values of these constants may be found out by using the end conditions. So while differentiating, while integrating, the two constants C1 and C2 will get. So the values, you have to calculate the C1 and C2 by using boundary conditions, that is constraints. After that, substitute these two, C1 and C2, in this integral equation, you will get a slope and deflection. The first one we will get from this equation slope, and second one we will get deflection. So now we will see for simply supported beam with a central point load. So this is a simply supported beam. You know, these two ends are supported, A and B, and at C the load is acting at its midspan, W by 2, W by 2, and then L by 2 and L by 2. So the distance. So take one section, cross section with the distance x. Consider simply supported beam AB of length L and carrying a point load, that is W, at the center of beam C as shown in figure. From the geometry of the figure, we find that the reaction at A. First calculate the reaction at A. So here you can see in this figure, this is a deflection at point C. Now the reaction at A and B are RA is equal to RB is equal to W by 2. So why? Because the load is acting at its center, so that the vertical loads equal to upward loads. downward loads and upward loads equal. Ra plus Rb is equal to W. So consider a section X at a distance small x from B. We know that the bending moment at this section, calculate Rb multiply with x. So W by 2 into x, that is Wx by 2. The plus sign due to sagging. Consider a section x at a distance x from B. We know that the bending moment at this section mx is equal to Rb into x. That is W by 2 into x, that is Wx by 2. Therefore, the bending moment at say x, already we know that m is equal to ei into d square y by dx square. So at x section, mx is equal to ei into d square by dx, that is equal to wx by 2. So integrating the above equation. So now integrate this equation. Integrate e into d square by dx square is equal to integral wx by 2. Now the after integration ei take outside constant, and then d square y by integral d square y by dx square is equal to dy by dx. That is equal to w into x square by 2 into 2 plus c1. C1 will get here from the first integration. So again do the integration, double integration. The C1, where C1 is the first constant of integration. So we know the boundary conditions. First apply the boundary conditions, we will get C1 value. Clear? So both the boundary condition at x is equal to L by 2. Then dy by dx of slope is equal to 0. As the maximum deflection is at the center, hence slope at the center will be 0. So substituting these values in equation 2. So what is this equation? 2 ei into dy by dx is equal to w into x square by 4 plus c1. So that here the dy by dx is 0. So that ei into dy by dx is equal to 0 into x is equal to L by 2. Wx square by 4. You will get WL square by 16 plus C1. Here C1 you will get minus WL square by 16. So substituting this value of C1 in equation 2. So the 2 equation is ei into dy by dx is equal to Wx square by 4 plus C1. Now C1 calculated, the value is minus WL square by 16. So substitute Wx square by 4 minus capital WL square by 16. So this is the required equation for the slope at any section. So it will be interesting to know that the maximum slope occurs at A and B. Thus, for maximum slope at B, substituting x is equal to 0 in equation 3. So the maximum slope occurs at A and B. So as per diagram, The maximum slope occurred at this point, theta 1 and theta 2. So that the maximum, the substituting x is equal to 0 in equation 3, the above equation. So now you will get EI is equal to IB into WL square by 16. EI. So now, what is the slope at B point? That is minus WL square by 16 EI. Or in radians, WL square by 16 EI radians. By symmetry, at A section, at A point, the slope is IA. That is WL square by 16 EI. So IA is equal to WL square by 16 EI and IB is equal to WL square by 16 EI. So here negative sign. Why the negative sign here? The minus sign means that the tangent at B makes an angle with AB in the negative or anti-clockwise direction. The tangent at B makes an angle with AB as shown in figure here in anti-clockwise. Clockwise. So that's why the IB is negative. Clear? Integrating the above equation. So first you will get here, you got slope at A and B after completion of first integration. In this C1, first constant of integration already we calculated. And then integrating the equation once again, that is EI into Y is equal to WX cube by 12 minus WL square by L square into X by 16 plus C2. EI into Y WX cube by, so 3 equation, take this one, EI into dy by dx is equal to WL square by integrating. So you will get EI into Y. EI into Y WX cube by 12 minus WL square into X by 16 plus C2, where C2 is the second constant of integration. So we know that when X is equal to 0, then deflection Y is equal to 0. Substituting these values in equation 4, we get C2 value. Where C2 is the second constant of integration. We know that when X is equal to 0, the deflection 0, substituting this equation, 4 gets C2 is equal to 0. So now, you got value EI into Y after substituting C2 value, WX cube by 12 minus WL square into X by 12. So this is the required equation for the deflection at any section. So a little concentration will show that the maximum deflection occurs at the midpoint C. Thus the maximum deflection substituting X is equal to, well, in equation 4. So in equation 3, so deflection occurs at midpoint C, so that the substitute X is equal to L in equation, above equation. So EI into Y is equal to WL cube by 12 minus WL square into L by 16. So after simplification, WL cube by 96 and minus WL cube by 32 is equal to minus WL cube by 40. So at C, the deflection we got minus WL cube by 48 here. So minus sign means that the deflection is downwards. So we got deflection at C, WL cube by 48A, and the slope also we have calculated. For concentrated center point load, simply supported beam with a concentrated load, the WL square by 16 EI. WL square by 16 EI is the slope. Deflection is, the maximum deflection is WL cube by 48 EI. These are the equations for a simply supported beam with a center point load by using double integration method. Now, we will see simply supported beam with a uniformly distributed load. So here, simply supported beam taken, length is L and carrying UDL, uniformly distributed load. So here also same procedure applied. Take X section with a distance small x from its B end. Consider a simple supported beam of length and carrying a uniformly distributed load of our unit length. From the geometry of the figure, we know that the reaction at A, first we calculate RA and RB. So here RA plus RB is equal to WL. Why? Because here the type of load is UDL. So the UDL load converted into point load. So that's why capital W is equal to W into L by, sorry, W into L. So RA plus RB, RA plus RB is equal to W into L. Now calculate reaction forces at A and B. RA plus RB is equal to WL by 2. So consider a section X at a distance small x from its B. We know that the bending moment at this section is W into L x by 2 minus WH square by 2. So now write down the mx, the bending moment at x, EI into d square y by dx square is equal to Wx by 2 minus WH square. Now integrate this equation, you will get slope. So you get C1 constant and find out the C1 constant by using boundary conditions. So integrating the above equation. So that equation is EI d square y by dx square is equal to WLX by 2 minus wx square by 2. So integrate this equation. So that the d square by y dx square term is dy by dx. Ei is the constant, and wx square by 2, and you will get wx square by 4, and similarly here wx cube by 3. So here integral ei d square by dx square is equal to integral wx by 2 minus wx square by 2. So you will get this equation with the constant c1. Where c1 is the first constant of integration. We know that the x is equal to L by 2 and dy by dx is equal to 0. Substituting these values in the above equation, dy by dx is equal to 0 and x is equal to L by 2. So substitute in the above equation, 0 is equal to w into L by 2 whole square by 4 minus w into L by 2 whole square by 6 plus c. Substituting these values in the above equation, you will get c1 wl by 4 into L by 2 whole square minus w by 6 into L by 2 cube plus c1 wl cube by 16 minus wl cube by 48. So after simplification, the c1 is minus wl cube by 24. Now substitute this value in a second equation. The equation is ei into dy by dx is equal to wl x square by 4 minus wx cube by 6 minus wl cube by 24. After substituting the c1, before substituting the c equation is di into dy by x dx is equal to wl x square by 4 minus wx square by 6 plus c1. So after substituting, we got this equation. This is the required equation for the slope at any section. We know that the maximum slope occurs at A and B. Therefore, the maximum slope, substituting at A and B, say at suppose this is simply supported beam A and B. At this section is x with small x distance, the x is equal to 0. In equation 3, so substitute the x is equal to 0 in this, 0, 0. Therefore, ei into dy by dx is equal to minus wl cube by 24. So the dy by dx is, you can write, that is the slope of the beam at point B, that is theta I B or theta B. Therefore, the slope is at B is minus wl cube by 24 E. So the minus sign means that the tangent at A, it makes an angle with the AB in the negative or anti-clockwise direction. So this is theta B or IB, that is equal to minus wl cube by 24 E. So now integrating the equation once again, so you will get deflection EI into Y is equal to small WL into x cube by 12 minus WX x to the power of 4 by 24 minus W del cube into x by 24 plus C2, where C2 is the second constant of integration. We know when x is equal to 0, then y is equal to 0. Substituting these values in equation 4, we get C2. Substitute x is equal to 0 and y is equal to 0. So, the C2 will get 0. Therefore, substitute C2 is 0 in this equation. You will get EI into Y is equal to WX cube by 12 minus WX to the power of 4 by 24 minus W L cube into X by 24. So, this is the required equation for the deflection at any section. We know that the maximum deflection occurs at the midpoint C. Thus, the maximum deflection substituting x is equal to L by 2 in equation 5, that is above equation, the deflection occurs at point C. So, what is the point C distant value? X is equal to L by 2. So, now substitute x is equal to L by 2 in this equation, substitute. So, now you can write EI into YC is equal to WL by 12 into L by 2 whole cube minus W by 24 into L by 2 to the power of 4 minus WL cube by 24 into L by 2. So, in this equation L by 2 substitute. So, after simplification you will get 5W L to the power of 4 by 384 EF. So, this is the final equation deflection 5W L to the power of 4 by 384 EF. Here minus sign means that the deflection is downwards. Note, the above expression for slope and deflection may also be expressed in terms of total load, such that W is equal to capital W is equal to small w. So, the slope equation is, so already I have written here at B and A. At B, WL cube by 24 into A. At A, WL cube by 24 into E. Why? Because due to the symmetry, they both are same or simply supported beam at their ends. The slope is equal. So, the slope and deflection may be expressed in terms of total load. The total load is W into L. So, you can write again this equation WL square by 24 EI and 5W cube by 384 EI. Previously, 5W L to the power of 4 by 384 EI. So, now you can write W is equal to WL. In place of W is equal to W. So, now here you can W into L cube into L. So, you can substitute W into L is equal to capital W. So, that the equation you can write 5W L cube by, so capital W by 384. Here also capital W L square by 24A. So like this, have to calculate the slope and deflection of simply supported beam with concentrated load and with uniformly distributed load by using double integration method. So first you integrate the equation, differential equation, you will get slope, and then second integration will get deflection. After calculation of C1 and C2, the constants, and then substitute these values in their equation, and then you will get the final equations for a slope and deflection equations for a simply supported beam or any beam. So here we have taken a simply supported beam. You can calculate for cantilever beam. Simply supported beam with eccentric load. Cantilever beam with UDL. So same procedure you can apply and calculate. So these are the references I have taken for this PPT. S. Ramamrutam. The title of the book is Strength of Material. And the second one is R.K. Rajput, Strength of Material title. The other is R.K. Rajput. Another one more other R.K. Bansal, a textbook of Strength of Materials. And publishers are Lakshmi Publications, and edition is 2009. So latest edition also available. You can refer. And R.S. Kurmi and Gupta. The title of the book is Strength of Materials. Publishers are Chand and Co. So take any one book for reference. You will get more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.